Hi, I'm Kim Kenny with the Crewe Astronomy Club, and welcome to Part 5 on Telescopes Part 2. In this lesson, we're going to be talking about the different types of telescopes and their mounts, navigating the night sky, and basically what to buy. Because if you live in a city or suburban area and cannot get out into the country and out to a deep sky location, well then consider getting a small refractor or reflector, even something like this that fits on a patio top or tabletop somewhere, or picnic table. You can enjoy viewing the night sky, even the planet and the moon, and some deep sky objects as well. But a great way to get started. Also, we're going to be talking about the different types of eyepieces as well, because you don't want to buy a telescope that advertises way up high in power, like we mentioned before, and also ones that offer 0.96 eyepieces. These are the ones we want you to avoid. Look for telescopes that advertise 1 1/4 inch barrel eyepieces. Now the 1 1/4 is how big they are from here to here in diameter. So here, look at the difference between the two. Barely looking through a pinhole as opposed to a really nice view up in the night sky. And if you get a telescope that maybe is 5 inches in diameter or more, you may even have not only the 1 1/4 option, but the 2-inch eyepiece option as well. And this is where you really get to see the night sky. Look at the view opening, and this is an eyepiece, how wonderful it is to look at the night sky, and how much bigger it is than the 1 1/4 inch, which of course is definite, but avoid the 0.96. So let's get started on Telescopes Part 2. So the questions asked at Virginia State Parks are, how do you aim your telescope? Can you automatically track objects with a Dobsonian telescope? What's a finder scope? And can I adjust the height from my wheelchair? And what's the difference in telescopes and their mounts? Well, these questions we're going to answer for you in Lesson 5. So first of all, telescope types and mounts. The ones on your left are your equatorial and fork mounts, which track objects in the sky as the Earth rotates. The telescopes on your right are your alt-azimuth tripod, where you point, aim, and observe and adjust as the Earth rotates, same as the Dobsonian telescope. Your equatorial mounts on your left take around 30 minutes for setup time. Alt-azimuth or Dobsonian around 5 minutes. So why an equatorial mount? People ask us all the time, why the more difficult mount? And that's because beyond 200 power, you will be constantly adjusting your telescope to track an object to compensate for the Earth's rotation. We're spinning pretty fast, and here's your telescope's field of view. So an 8-inch Dobsonian, set at 400 power, has just seconds of viewing before your target is history. I get this beautiful shot of Saturn, tell you to take a look at it, and as soon as you get a look, you say, well, I saw something for a second, and now it's gone. It's completely gone. So, how do Maksutov-Cassegrain telescopes work? It's pronounced Maksutov, or MAX for short. You have your eyepiece, your focus knob, your main mirror. Notice there's a hole in the back of it, a corrector plate lens, secondary mirror. Light enters, bounces back and forth between the lenses and mirrors. This gives a credible focal length. So MAX are popular for power and portability. These short tube lens and mirror combinations give outstanding views of the planets and the moon. Look at the focal lengths, 1530 and 2270, and there's your finder scopes, which we'll be talking about in just a little while. So an equatorial mount with a tracking system is necessary when you plan to observe an object for an extended period of time, and we're talking at least 2 to 3 hours, or you're an advanced amateur astronomer into astrophotography, which can require tracking an object all night to get that perfect photo of a distant galaxy, nebula, or cluster. So for advanced astronomers, setting up a Maksutov-Cassegrain telescope on an equatorial mount. So there's several steps. So first, we'll set your latitude from where you're observing. Now you just have to set this once unless you're traveling north or south. Then we face the tripod north. Next, the tripod must be completely level. So get your level, put it in both directions, keep that bubble dead center, and adjust the legs if necessary. Then we add the counterweights for balance. Then we lock down the clamps and attach the telescope. Now we attach the diagonal, the eyepiece, and the finder scope. Then we attach the power supply and controller. So now we just adjust the tube and weights for perfect balance so the telescope pivots easily. As you can see, I'm moving the telescope up and down, left and right. The weights go up and down and the telescope can move up and down the dovetail bracket. Once it's completely balanced, now I can move the telescope in any direction from east to west, north or south. The tripod is facing north the whole time, but once it's perfectly balanced, you can see here that all I have to do is barely touch the scope and it's completely balanced. After it gets dark, I release the lock pins, if necessary, and pivot the base to center Polaris. Now all equatorial mounts have to be perfectly aligned with Polaris to track objects manually or automatically during the night. So how do Schmidt-Cassegrain telescopes work? Well, just like a Maksutov Cassegrain, you have your eyepiece, your focus, your main mirror, your corrector plate, and your convex secondary mirror. Light enters, goes back and forth, and gives this telescope tremendous versatility. And that's because these things come anywhere from 4 inches in size and diameter all the way up to observatory. So this 8-inch short tube lens and mirror combination are great for deep sky and planetary views. Your focal length 2,230 and a very nice finder scope on the side as well. So here's your Schmidt-Cassegrain on a fork mount tripod. As with the equatorial mount, you have to set your latitude once by moving the bolt and your wedge, level the tripod, and then to move this, you just loosen the 3 bolts attached to the wedge to slip off the fork and tube for easy transport, because this telescope basically just comes in 2 parts. Then we do the polar alignment. So as the Earth rotates, the scope keeps Polaris centered. So now we're focused on Polaris. Notice the forks are in the direction of where Polaris is. Once you're perfectly set, now the telescope can go east to west, move left and right, up and down, and go to any object we want to in the night sky with its tracking capability. Very easy and a very elegant way to track objects in the night sky. Once we have our target located, we lock it in, the motors take control, and then out in the field, you see we have this perfectly level. And then where is north? Well, in the direction of the forks. So in the direction of the forks is where Polaris is located. Now this is one of our favorite types of tripods. Your altitude plus azimuth equals alt-azimuth tripod. The telescope attaches to the tripod by sliding the dovetail bracket into the clamp. So I can use this small max scope on any type of tripod and swap off different telescopes. So just move the telescope to your target, lock the clamps, and adjust as needed. So as you can see, I'm moving the telescope north, south, east, or west, or azimuth. Then the altitude, move it up and down in any direction I want. Very simple, no complicated setups or anything, no balance weights. The thing actually balances itself. Then once I lock down the clamps, I can move the telescope by using the fine-tuned knobs and adjust as the gears. So other questions that are asked: can I adjust the height of the eyepiece so I can view from my wheelchair? Well, fork mounts and alt-azimuth tripods, as shown here, work great in keeping the eyepiece and telescope knobs level so the observer can view from a stationary position. So how do refracting telescopes work? Now refractors go way back to Galileo, back in the 1600s at 1609, where you have your focus, your eyepiece lens, your telescope tube, your objective lens, and your path of incoming light. Your very simplest type of telescope. These go from anywhere from ½ inch, very small, all the way up to about 6 inches. You won't see many other longer telescopes than that. So short tube refractors are great for star clusters, galaxies, and nebula. Long tube refractors have the sharpest views of the moon, planets, and small clusters. You can see the difference between the wide field and the short field telescope, and they both have their finder scopes so you can lock in on your target. So here's Keith's 5-inch refractor of the Crewe Astronomy Club. As you can see, at just 5 inches, it's pretty big. So why home refractors don't go beyond 8 inches of aperture in size? Because the size would be tremendous. An 8-inch refractor would be this size. So this is why you have some compound telescopes as an 8-inch Schmidt-Cassegrain in comparison how much smaller and more compact. So how do reflecting telescopes work? Well, you have your main mirror, your main tube, your eyepiece lens, your focus, and your secondary mirror. Light enters through the tube, off the main mirror, into the secondary mirror, and right up through the eyepiece. These are wonderful telescopes. As you can see, the light bouncing back and forth to it. So we have short and long tube reflectors, same as refractors. They're great for star clusters, galaxies, nebula, and planets. One's on an equatorial mount, and then you have your Dobsonian mount. So note, with a reflector like this, you get the most telescope for the money because mirrors are less expensive to manufacture than lenses, so you get the best telescope and the most for the money. So people ask us, can you automatically track objects with a Dobsonian telescope? Well, actually, this type, called an Intelliscope by Orion Telescopes, just punch in an object like M35 and the controller's directional arrows will point the way. The database contains 14,000 solar system and deep sky objects. So here's two tabletop Dobsonian mounts. Notice this small little refractor on a Dobsonian mount, little tabletop mount, so I can move it in any direction and enjoy in just a few seconds from my own backyard. Or this 90mm Mac scope. Just set the Mac to Polaris, lock the gears in, and turn on. So this little Dobsonian with a Mac scope on does track things in the night sky. I lock in the gears, turn on the controller. Now I can move the telescope in any direction using the motorized drive, up, down, left, and right, like Alt-Azimuth, as you can see the controller on your right, the simple arrows, and the speed controller where you can find anything up in the night sky, and it will track as the Earth rotates. Another great telescope for beginners is the 4.5-inch SkyQuest Dobsonian telescope. This one also from Orion Telescopes and Binoculars. As you can see, my lovely wife Margaret, this one kids really love. She can move it up and down, comes in one piece, and kids really love this telescope. So what's the best way to aim your telescope? Well, there's actually 3 ways to aim your telescope. With an equatorial or fork mount, you can align your scope north, point to a target with your finder scope, lock in the gears, and let the telescope track automatically if equipped, or just move it manually. The second way with an equatorial mount is right ascension RA and declination DEC. Now this is for the more advanced astronomer with tracking equipment on their telescopes. But briefly, just as the Earth has longitude and latitude grid lines to find your location on Earth, well, the celestial sphere also has a grid with degrees, hours, minutes, and seconds, which rotate around the North Star Polaris. So surrounding the Earth is a full grid with everything with an ID number on it. So every star and deep sky object has a right ascension and declination coordinate, which never changes. The planet's coordinates are always changing, however, due to their constant motion in the solar system. So now for an example, finding M4 in Scorpio using right ascension and declination. Use a star chart or smartphone or laptop or any computer software and it'll say right ascension 16 hours 24 minutes, declination -26 degrees. So your right ascension coordinates are located right there on the fork mount, your time of day, your declination coordinates, your angle. And your right ascension and declination numbers are located on your equatorial mount and shown on your hand controller. The third and simplest way to aim your telescope is to use the altitude plus azimuth method, where straight up is 90 degrees and the horizon is 0 degrees. Use your planisphere, star hopping, and your finder scope to point, aim, and observe. So notice we're looking north. If you're looking straight up where our gentleman is, he's looking 90 degrees northwest, 45 degrees north, or he's looking northeast at 0. So people ask us, what's a finder scope? This is imperative when you're viewing this way. Your finder scope is a completely separate telescope. Sits on top of your telescope. Here's a 50mm finder scope with a diagonal, and you have 2 adjustment knobs right here. You'll use these adjustment knobs to get it right the first time. Now you'll look through this telescope, this small scope, put the crosshairs over your subject. Here's a 30 and 50mm finder scope. Then you have your laser dot finder, 2 adjustment knobs to make adjustments and an on-off switch. Now it doesn't shoot a laser beam, just a red dot as you see here. Put the dot over your target. Now your main telescope is locked in. So when you get a brand new telescope, first thing you're going to do is go outside. So step 1, aligning your finder scope. You do this during daylight hours. Focus and center the main telescope on a distant object. So we get this big electrical tower off in the distance. There's your main telescope view under high power. Next, Turn the finder scope adjustment knobs as we showed you until the crosshairs are centered over your target. So as I'm moving the knobs back and forth left and right, I do it until I get the crosshairs dead center of what my main telescope has. Here's my finder view under low power. So your finder scope is like having binoculars attached to your telescope to find your target quickly. Simply point your main scope, aim with your finder scope, and observe with the main scope. Step 2, find your subject, in this case M42, the Orion Nebula. Step 3, use your finder scope and put the crosshairs right over the fuzzy spot under Orion's belt. Then lock in the scope. Now we see this image at 10 power. Here's our finder view. Step 4, drop in a low power eyepiece in the main telescope and focus. Then step 5, try different eyepieces to get the best view. In this case, the trapezium, the stars that are inside the Orion Nebula. So what you center in your finder scope is now centered in your main scope. What I've locked in, bingo. There's my finder view. Now all I have to do is look in my main scope, focus a bit, and there's my main view. This makes it so easy to find things in the night sky. With a red dot finder, we move the telescope, put the red dot right where we want it, and then we look at our main telescope. There's our main view, and there's a big, beautiful image. And a lot of fun. Some people actually have both on their telescopes, and it just makes it so much easier to find things in the night sky. Here, Polaris is north at 37 degrees altitude. We go at 37. Remember, 0 is on the horizon, locked onto it, and you got it. So tonight, star cluster M4 is located south-southwest at 24 degrees altitude. There's southeast, south, and southwest. South-southwest is in between the two, and we need to go up 24 degrees. So now, as we look up 24 degrees, in between the two arrows and right under Scorpio, we're going to put our spotter scope right under Scorpio, and there's that big, beautiful image of star cluster M4. So now that we've seen M4, let's try to find M57 and M51. I've got the planisphere and I've got the red flashlight. So we're all set to do some deep sky observing. Well, first we're going to find M57. We found Cygnus the Swan, Draco the Dragon, and they're both going to point to Lyra in the middle. And the first thing we're going to find is Vega, the blue giant star. So now as we go outside, all the constellation lines have disappeared. But we did find Vega. There's Vega again, and there's the two stars on the end of Lyra the Lyre. Directly overhead, we see Vega again. Remember, the lines don't exist. So up in the night sky, we're going to focus around these two stars here with our finder scope. So now we're going to take our finder scope and move it at 10 power. This is our finder scope at 10 power, and in between those two, you can see a little fuzzball. You got it. That is the thing that we're looking for right there. Now we look at our main telescope and we focus, and now we see M57, a planetary nebula, magnitude 9.50, and distance from Earth 2,300 light years away. So let's find another deep sky object beyond human sight. This is a tough one, but so rewarding when you find it. Find M51, the Whirlpool Galaxy. Best to do in the middle of summer with this one where it's directly overhead. We know it's in the Big Dipper, so we make a 90-degree angle from the first and third star and the handle of the Big Dipper. There's the first star, there's the third star, and we want to make a 90-degree angle to our star chart. This is where we want to put our finder scope. So now that we go outside, we find the Big Dipper and the area to find M51. That's where we're focused on. So now at 10 power, we're zooming in with your finder scope at 10 power. There's the first star, and now the third star is way down here, bypassing, of course, Alcor and Miser, the double star in between the two. There's where we want to put our finder scope, and there's a little fuzzball right there, highlighted in red. So now when we zoom in, still at 20 times in an 8-inch telescope on a moonless night and almost directly overhead, little fuzzball, we zoom in a little bit tighter to 50 power. So increasing to 50 times, there's the Whirlpool Galaxy, magnificent, magnitude 8, and distance from Earth 37 million light years. So people ask us, how did you get started with Virginia State Parks? Well, this article from Sky and Telescope magazine, Where Are the Young Astronomers? And what does it take to draw today's youngsters away away from the television and out under the stars. And this article was done in September of 2000. So we went to Virginia State Parks. We've done programs with the Boy Scouts, Girl Scouts, 4-H clubs, homeschoolers, church groups. And with articles like this, the Crewe Astronomy Club focused on a hands-on approach to astronomy. So nothing gets you more excited than exploring the night sky and discovering something on your own. Here we're looking at some solar observing, a special telescope for that, 4-H club as you see here, and of course the Girl Scouts, getting them out there and teaching them all about the night sky. But I couldn't have done this without Keith Johnson. He's been with me since 1998 with the Crewe Astronomy Club. He's a school teacher. He has covered multiple subjects like astronomy, physics, ancient history, government, and law. Main interest to talk about galaxies, the lives of stars, black holes. We couldn't have the Crewe Astronomy Club without Keith Johnson. So he's been my right-hand man, so thank you very much. Couldn't have this program here without his work and input. Then my lovely wife, Margaret. She's an IT person for Virginia Tech, has 4 telescopes of her own, and loves to work with the younger children when we do our programs. She's taken almost all the photos at the horizons and sunset that you've seen in these presentations, and also enjoys metal detecting and painting as well. Then there's me, Kim Kenny. Since 1990, I've been working with computers and graphic art design, and 12 years as a former radio announcer gave me the tools to put this presentation together. So when I was 15 years old in 1973, I bought an $18 tabletop telescope and could see the rings of Saturn. That's what got me hooked on astronomy. So before we conclude Lesson 5, consider these 3 final thoughts. Remember that astronomy is a universal hobby. Everyone around the world enjoys looking through a telescope. Seeing Saturn's rings or the moon close up is like seeing the ocean for the first time. So if you have a telescope, share your experience. Also, telescopes are time machines. The further you look back into space, the farther back in time you're observing. The sunlight that you see and feel left the sun 8.5 minutes ago. Red giant Betelgeuse in Orion you're observing 428 years ago, because Betelgeuse is 428 light years away, and it took that long for the light to reach us. Or consider M31. You're actually observing the Andromeda Galaxy 2.2 million years ago. Finally, amateur astronomers make valuable contributions to the scientific community. They have discovered new comets, tracked asteroids, and often join professionals which require photos and data from all over the world. And you can be a part of all this. I hope you've enjoyed these lessons. I'm Kim Kenny, and on behalf of the Crewe Astronomy Club, clear skies, and thank you for watching.